Welcome to Summarize Science. Building a massive artificial intelligence model is like planning a multi-million-dollar construction project, and you need a blueprint before you start. In the world of AI, these blueprints are called scaling laws, which help researchers predict how a model will perform as it gets bigger. However, creating these blueprints has become a massive budget allocation problem rather than just a simple first step. Currently, fitting these scaling laws can itself cost millions of dollars because it requires running hundreds of smaller pilot experiments. The paper we are looking at today proposes a way to spend less while fitting these laws better through active experiment selection. As seen in Figure 1, the researchers' method can identify the best training settings using only a tiny fraction of the original budget. On certain tasks, they reached the optimal low-loss region using only 1% of the usual training budget. The core problem is that researchers usually hand-select their pilot runs or just run a bunch of random small versions of the model. This is inefficient because not all small experiments are equally good at predicting what happens at a massive scale. The study formulates this as a budget-aware sequential design, meaning the computer picks the next experiment based on what it still needs to learn. The method works by looking for what the authors call basins, or different plausible ways the scaling law might fit the data. By measuring the uncertainty between these different versions, the system can target experiments that specifically clear up confusion. This is broken down into two parts: intrabasin utility, which refines a specific guess, and interbasin utility, which helps choose between totally different guesses. They tested this new approach across a diverse benchmark of 65 different scaling law scenarios. These tasks included things like tuning hyperparameters, data allocation, and even how models perform as they get more sparse. This wide variety ensures that the method isn't just a one-hit wonder, but works across many types of AI development. The results shown in Table 2 are quite impressive, comparing the new method against 5 standard baselines. In almost every category, the new uncertainty-aware method delivered the strongest performance for the lowest cost. For many tasks, the method approached the accuracy of using the full dataset while only using 10% of the total training cost. This proves that being smart about which data you collect is far more important than just collecting as much as possible. One fascinating finding is that sometimes this budgeted method actually outperforms fitting a law on all available data. This happens because blindly fitting every data point can sometimes confuse the model about the high-cost region that actually matters. As the visualization in Figure 3 shows, having a low error on cheap, small points doesn't always mean you'll be right about the expensive, large ones. To summarize, researchers have developed a way to make AI development significantly more efficient by treating experiment selection as a budget problem. By using an uncertainty-aware strategy, they can recover accurate scaling laws from only a small fraction of the usual training runs. This means that in the future, accurate scaling law fitting won't just be for the companies with the deepest pockets. Instead, it will be treated as a precise modeling problem where every dollar spent on a pilot run provides maximum information. This could lead to faster breakthroughs and more specialized AI models that are perfectly tuned for their tasks without wasting millions on the way. Thank you for watching Summarize Science, and stay tuned for more breakthroughs made simple.